Good.
Okay, so if we're going to be calculating the distance that Marley actually walked, it's important that I figure out what formula to use. And so when I start thinking about this, we had learned in the last video for last week that circumference, the formula for that is 2 pi r. Keep in mind that this 2 pi r is saying that whatever my radius is, so from the center to the actual circle itself, if I multiply that distance by 2 pi, which is the full rotation of a circle, then that would give me this whole length around the entire circle. So that's great. However, Marley was being lazy today and she didn't walk that full rotation of the circle. She only walked this distance right here, highlighted in yellow. So I need to figure out how far she actually walked. If I think about the whole picture, I can think, well, what would have been the whole distance of the whole rotation if she did walk that full rotation? So our circumference would have been 2 pi r. Marley's wheel actually has an entire diameter of 4 feet. So if I were to look at a line straight across like this, that would be a 4-foot diameter, which means that half of it would end up being 2 feet. So if my diameter is 4 feet, that means that my radius is only 2 feet. So the entire circumference, if she did walk that, would be 2 pi times the radius of 2 feet. If I multiply these two numbers together, I would get 4 pi feet for my circumference. But usually we don't use pi when we're talking in real life about distances like this. So if I multiply this in a calculator, a nice calculator to go to if you don't have one that has pi in it. I think a lot of your phones do, but if you don't, desmos.com/scientific has a really nice calculator that you can use. So let's jump to that. So coming over to this Desmos calculator, I can type in 4 times pi, and it'll give me about 12.566 feet. So going back to my calculations here, I can say that Marley walked about this far. So we'll say about, let me write this little squiggly here, about 12.566 feet. So again, when she walks that full rotation, she's walking a little bit over 12.5 feet. But she didn't walk that full distance. So now let's take a minute to think about how we could calculate just this arc length. So this part of the video is really calculating arc length. Let's make this a little bit bigger so it stands out to us. Arc length. So the length of the arc that she just walked. So notice if she did a full rotation, that would have been a 360-degree rotation. But she only did part of it. So really what I need to do is figure out the measurement of this central angle. How many degrees did she actually walk? So to do that, I'll need to get out one of my math tools, my protractor. It's been a while since we've used this. If I put this at the center of the circle and I rotated this around so that the first part of my sector lines up here with 0 degrees, I can start to count up 10, 20, 30, 40, etc., all the way till it gets over here to this 140 degrees. So the central angle that Marley walked is 140 degrees, not the full 360 degrees. So let's go ahead and write in there 140 degrees. Lucky for me, she walked a nice even angle there. So looking at this, I want to think about the circumference of only this 140 degrees. So that leads us to our actual formula for arc length, which is the 2 pi r for the circumference, but this fraction really represents the fraction of the circle that she walked. So keep in mind that this theta up top is really just a variable, and that theta represents the central angle measurement. So we measured that central angle to be 140 degrees. So now let's take a look at our arc length measurement. So we've got 2 pi r, which was the 4 feet, or 2 feet rather. And then my fraction out of the 360-degree rotation was really only 140 degrees. So I'm going to take all of this and plug it into my calculator, my Desmos calculator, just so you can see kind of how I would do that. The only thing, I'm going to type it all in together. The only thing I'm not going to type is the feet. So I'll put the feet at the very end of my answer. So let me write some squigglies here to say that this is going to be an approximate answer. So going over to Desmos, I'm going to say that I've got the 2 times the pi times the 2-foot radius times, and then remember we've got this fraction 140 out of 360. So I'm going to put parentheses in there, 140 divided by 360. Notice we've got all of that in together. The only thing missing is the feet. So when I hit enter, I've got this about 4.8869. I'm going to say round it to the hundredths place, so 4.89. So we can say the distance that Marley actually walked is about 4.89 feet. So almost 5 feet, not very far. She was being really lazy that day. But luckily for us, it helped us calculate a part or an arc length of a circle. So I hope that made sense. If you have any questions, be sure to let us know. But we've got a couple questions about this for you to practice on your own.
So I'm going to find the area of this pizza and cut it into slices and find the area of those slices. Before I do this, though, I'm going to need to measure the diameter of this circle for later use. So here I have some measuring tape that I had lying around. And remember, the diameter is straight through the center. This is a Little Caesars pizza, so they cut it a little off. But I'd say this pizza has a diameter of about 14 inches. Next, I'm going to cut along the diameter of this pizza to slice it in half. So I'll just go with their line, do it a little bit better. So here I am going through the middle, along the diameter, right through the middle, to cut it in half. So when you have half of a circle, this is what's known as a semicircle. Dang it, I always say it wrong. Semicircle. Half of a circle is known as a semicircle. I am also going to cut this semicircle in half again to get us what is known as a sector. A slice of pizza is known as a sector. So here I have cut it into fourths. And the reason why I use pizza as an example is because I associate the definition of a sector as a slice of pizza. Of course, I will get into the technical definition shortly, but for all intents and purposes, a sector of a circle is just a slice of pizza.
Okay. Well, now that I've eaten that delicious lunch, let's go ahead and take a closer look at sectors. So first up, our geometric definition. A sector of a circle is a region bounded by 2 radii of the circle and their intercepted arc. So for those of you who don't know, radii is the plural for radius. And if you were to look at the sector over here on the right, this top radius and this left radius act as a boundary for this arc. So that's why it's called an intercepted arc. Those 2 radii intercept the arc. And since our diameter was 14 inches, a little less, it was a Little Caesars pizza, a little less, but 14 inches was our diameter. Radius is has half the length of the diameter. So our radius will be 7 inches. So, how does the area of a circle compare to the area of a sector? Well, to find the area of a circle, you take pi and you multiply it by r squared. Pi times the radius squared. So for this pizza, our area is pi times, I prefer to use parentheses, 7 squared, which 7 squared is 49. So I'll write that as 49 pi. That is the exact answer. Sometimes you'll want to leave the answer exact like that, because pi is not 3.14. But if you're asked to round, plug in pi into your calculator at the very end. So 49 times pi, which is, I'll round to 2 decimal places, it's about 153.94. So that's about 153.94. Can't forget though that this is area. Should always include our units. So this is inches squared. So that's how many square inches a Little Caesars pizza is. So me, I always prefer to slice pizzas into fourths. I don't know why. Anyways, so same pizza, same radius, but I ate a fourth of a pizza for lunch. So if I want to find my new area, I just take that ratio, the 1/4, and then I multiply it by the 49 pi. You should always simplify if possible, especially if you're being asked to give exact answers. 49 times 1 is 49. And 4 times, there's an invisible 1 in that denominator. So my exact answer is 49 pi over 4. There's no way to simplify that, but I'll plug it into the calculator. Ooh, that was weird. Good enough. So 153.94, and all I'm going to do is divide that by 4. Which means that I ate 38.48 inches of pizza. I ate about 38.48 inches squared of that pizza for lunch. But you may be wondering, I knew that this was a fourth. How are you going to know what that fraction is? And what about people who eat half a pizza, who don't cut slices the way I do? So what I've done here, I created a y-axis and an x-axis on top of my pizza. I labeled the center of the pizza as O for origin, just like the coordinate axes. So if this is my center and I know that I ate a fourth of the pizza, that's 1 quadrant. 1 quadrant is 90 degrees. And we know that all 4 quadrants, an entire rotation, in fact, I can show you that. Math tools, compass. If I were to put this on the center, yeah, pretty decent. A full circle is 360 degrees. So if you don't know what angle has been chopped off, you take the 90, because that was the slice that I cut, 90 degrees worth, but it's out of 360 degrees. And 9 goes into 36 4 times. So 9 over 36 reduces to 1/4. And that's where the 1/4 came from in my previous problem. So if we were going to generalize it for any given circle, to find the area of the sector is the exact same formula. Pi times r squared, but I'm going to generalize this right here. All circles have 360 degrees, so we just need to come up with a variable for the slice that you're looking for, the piece that you've cut out. So I usually use theta. I prefer theta. For this one, though, I'll leave it as m for measure. It doesn't matter what variable we use. So 90 over 360 is what got me the 1/4, but your angle could be anything. So you use the same circle formula, pi r squared, times whatever angle you've been given, divided by 360 degrees total. You can further see this 1/4 ratio by comparing areas with other areas. So if I were to compare the area of my sector, that was 38.48. And divided by the area of the circle, that was 153.94. You want to use as exact answers as you can, but I think you'll get the point. If I wanted to know how one area compares with another, you create a ratio, you create a fraction. So since I'm wanting to know how much of the pizza did I eat, well, I already know I ate 1/4 of that pizza. But if you didn't know, you could take the area of your slice divided by the area of the whole. And 0.24999, yep. 0.25, which we know is 1/4, 1/4.
Well, here we are in the kitchen, and I'm going to make some roll-ups. And I'm going to use this tortilla that has a 5-inch diameter, and I'm going to put some cream cheese on it. Well, that looks yummy. Now I'm going to put some cream cheese on this bigger tortilla. This tortilla has a diameter of 10 inches. So if this one is 5, should be about halfway across. Yep, it's about halfway across. The diameter of this one's 10. I'm going to put some cream cheese on it. All right, that's looking pretty good. And hey, this one's twice as big as this one. Does that mean there's twice as much cream cheese? I wonder. Let's go investigate. Well, I don't know if you can tell from my Wonderful World of Disney ruler, but this smaller tortilla, I took a picture of it. It's 5 inches in diameter, and so diameter of the first tortilla is 5 over here on the left, which half of that would be 2.5, 2.5, so the radius is 2.5. The other one, the bigger tortilla, goes out to the end of Mickey Mouse's ear, which is at 10. And So diameter number 2 is 10, which half of that would be 5. So the radius of the second tortilla would be 5 here. And if you look at the second diameter, it is 2 times the first diameter. The ratio, diameter 2 to diameter 1, would be 2, twice as big. Same thing with the radius. Radius 2 to radius 1 would equal 2. The scale factor here is 2 between that tortilla and that tortilla. Scale factor on circular figures, circles are all similar because they're all the same exact shape, they're just different sizes. So this circle is similar to this circle and the scale factor is 2. Doesn't matter how you measure it, any length measurement will come out to have a ratio of 2 if you do large to small. But we're not looking at measurements. To cover the tortilla with cream cheese, I needed to cover the entire area, not just a length. And of course, area for a circle is pi r squared. So the area of the first circle here has a radius of r sub 1, radius of the first circle. The area of the first circle is pi times r sub 1 squared. Over here, the radius of the second circle, a sub 2, is pi times radius of the second circle, r sub 2 squared. So pi r squared here and pi r squared here. If we want to look at how these areas are related, though, we can come up with a way to combine them. Because here, the second radius, the thing we're squaring, is 2 times the first radius. So 2r sub 1 squared. And we're squaring the entire thing, which means we can square the 2 and square the radius. So it's pi times both of them squared, which if you rearrange this, 2 squared times pi times r1, this pi times r1 squared, pi times r1 squared, that's the area of the first circle. So the area of the second circle is not 2 times the area of the first circle, it's 2 squared times the area of the first circle, or in this case, 4 times the area of the first circle. And we can look at that for any scale factor. Here's just a random circle that is k times larger than the first one. R sub this nth circle that we're dealing with, the radius of this nth circle is k times the radius of the first circle. So here the k is the same thing as the 2 was back here on the second circle. And if you look at the ratio, this circle, any length in this circle is going to be k times as big. Radius to radius equals k, from this fact that the radius is k times the first radius. And if we look at the area of this circle, it's pi times the radius of this circle squared. We know the radius of this circle, the thing we're squaring, is k times the radius of the first circle, so that's what we're squaring. And again, we're squaring both k and r sub 1. So there's k and the radius of the first circle, r sub 1, they're both being squared. We can rearrange it. It's pi times this stuff, so pi times the first radius squared times k squared. There it is. This is the area of the first circle again. It's always going to be the ratio of the lengths, which is the scale factor again. The ratio of the lengths squared. That's what the ratio of the areas will always be. Which, going back to our original problem, how much more cream cheese is on the bigger tortilla than on the little tortilla? Well, the scale factor is 2 to 1 because the lengths are twice as long. Then the scale factor is 2 to 1. You square that, you get 4 to 1. There's 4 times as much cream cheese on this one as there is on this one.
So now we know. And this tortilla has a diameter of 8 inches. So if I cover it with cream cheese, there it is. 8 to 10 is, what, 8 over 10 would be 4/5. Does that mean it has 4/5 the amount of cream cheese? What would you have to do to that 4/5 ratio to figure out the ratio of area on this one, the cream cheese area to cream cheese area on that one? Are we really getting 4/5 the amount of cream cheese?
So again, comparing to the large one, the third tortilla to the second tortilla is the ratio of lengths I have going on here. That was 8 to 10, which reduces, the 2's cancel, make it 4 to 5, which is 80%. The medium tortilla is only 80% of the width of the larger tortilla. What you have to do to that, though, is square it. The ratio of lengths squared gives you the ratio of areas. So to get the total area comparison, it would be 4/5 squared, which you can square the 4 and square the 5, squaring them both. 4 squared is 16, 5 squared is 25, and 16 25ths is 0.64. So the medium tortilla, the third tortilla, only has 64%, not 80%, 64% of the cream cheese that's on the larger tortilla. Big difference between 80% and 64%.
And if my homework was to make this video, of course, I'm going to eat the video. Got some green chili, some orange peppers, and some green onions here. I'm going to make myself some roll-ups and eat my homework. And I hope you found learning about arc length, sector area, and k-squared, the ratio of areas compared to the scale factor, as delicious as I did creating the lecture for you. See you next time.